Hi, my name is Axel Apolonio Flores. This is our paper reading and presentations from the class Introduction to Computer Security. My title is Drone Security and the Mysterious Case of DJ's Drone. What is a drone? First, let me define what a drone is. A drone, also known as Unmanned Aerial Vehicle, UAV, is a remote pilot aircraft that can perform a variety of tasks without the need for a pilot on board. From its initially designed as a military tool to its proliferation in civil applications, drones have rapidly evolved in recent years, thanks to advances in sensor technology, artificial intelligence, and aircraft design. Application of drones. Now, let me explore some of the many ways drones are being used today. In agriculture, drones are revolutionizing how crops are managed, allowing farmers to monitor plant health, detect diseases and pests, and optimize the use of fertilizer and pesticides in a more efficient and sustainable manner. In the field of environmental conservation, drones are being used to monitor deforestation, climate change, and endangered wildlife. Their ability to collect detailed data from remote and hard-to-research areas is helping scientists better to understand our impact on the environment and develop more effective conservation strategies. So let's talk about DJI. DJI, or Dajian Innovation Science and Technology, is a Chinese company in drone technology and aircraft imaging systems worldwide. It was founded in China, in Shenzhen, with the vision of making drone technology accessible for everyone. DJI is known for its wide range of drones, ranging from popular customers model to high-end professional and enterprise solutions. For example, include the Phantom series, now for its ease of use and image quality, the Mavic series, who stands out for portability and performance, or the Inspire series, designed for professional air, cinematographic, and photography applications. So, recent investigations raises significant concerns about the cybersecurity of DJI drones and their potential to expose users to security risk. And this precise topic it was discussed today in the article. This article in question highlights the fundamental questions. Do DJI drones offer real protection for users? Researchers have discovered vulnerability in the software and systems of these devices that could be exploited by cybercriminals to access sensitive data, compromise the integrity of drones, or even take remote control of them. This vulnerability poses a dilemma for DJI drone users. Although these devices offer an intuitive flight experience and advanced features such as real-time transmission of images and videos, they may also pose a potential risk to users' security and privacy. The possibility of drones being hacked or compromised in some way raises serious concerns about their use in sensitive or critical environments, such as industry areas, government facilities, or public events. In response to concerns, DJI has taken steps to address security vulnerability on its product. So, what problem exists? Drones face considerable regulatory changes as regulation vary greatly from one country to another and can be confusing for operators. This disparity makes adherence to laws and ensuring safe and legal operation difficult. Additionally, collisions pose a fundamental concern in terms of safety, both of manned and unmanned aircraft. Despite advances in obstacle detection and avoid systems, the risk persists, highlighting the need for continuous focus on improved drone safety. Moreover, the emission of drones for illegal activities such as drug trafficking or smuggling in restricted areas present additional challenge for both authorities and public safety, underscoring the importance of robust prevention and enforcement measures. So, in this regard, the industry and regulatory bodies must collaborate closely to address this challenge and ensure a safe and responsible operating environment for drones. So the solutions. Now let's talk about some solutions that have been developed to address the mentioned challenge. For example, the first one, DJI Aeroscope. Aeroscope is a system developed by DJI for real-time drone detection and tracking. It enables authorities to monitor and track drones in airspace, providing crucial information about their location, identification, and flight path. This technology helps ensure safety in the sensitive areas and protect airspace integrity by detecting unauthorized drones and taking appropriate action as necessary. So, for example, the geofencing is a technology that uses global position systems to create geographical bounded virtual areas. These areas can be designed as restricted or prohibited flight zones such as airports, military bases, or densely populated urban areas. Drones are equipped with geofencing systems that automatically notify or prevent from entering for these zones, helping to prevent collisions and protect public safety. And finally, the hardware protections. Hardware protection solutions such as protective casings and physical security systems are designed to protect drones against external damage and unauthorized manipulations. These measures may include physical access locks, data encryption system, and manipulation protecting techniques, ensuring the integrity and the security of drones and their components. So, what did they do? The researchers approached the investigation in three distinct stages, each providing a unique insight into the security vulnerabilities in DJ drones. Firstly, they conducted comprehensive wireless analysis, focusing on study and manipulation the radio frequency used by drones. This approach allows the researchers to detect the drone position and the pilot's location by identifying radio signals emitted by the device and remote control. This information revealed the susceptibility of drones to interception and tracking, raising concerns about the privacy and security of data transmitted during the flight. Secondly, detailed static analysis was carried out, focusing on identifying vulnerabilities in the drone's firmware. This approach enabled the researchers to discover a technique known as firmware signature bypass, which allowed them to bypass security measures built into the firmware and access restricted or sensitive device functions. These potential vulnerabilities could be exploited by malicious actors to conduct cyber attacks or compromise the integrity of the drones and the data it collects. So, lastly, the last one, dynamic analysis was performed using the fusing technique, which involves subjecting the system to a wide variety of unexpected and random inputs to identify potential vulnerabilities and weaknesses in the software. This approach allowed the researchers to discover a total of 15 different vulnerabilities from authentication failures to programming errors, which could be exploited to compromise the drone security and its associated systems. This vulnerability underscored the importance of conducting comprehensive security testing on drones before the development in operational environments, as well as the need of effective mitigation measures to protect against potential cyber attacks and unauthorized manipulations. But with or without access. But before delving into these findings, it's important to understand the difference between passive attackers and active attackers, two types of actors that play distinct roles in cybersecurity landscapes. Passive attackers are individuals or entities primarily engaged in observing and gathering information without directly interacting with the target system. Using surveillance and passive listening techniques, these attackers can monitor and analyze communications between the drone and its remote control, seeking to identify vulnerabilities or sensitive information that can be exploited at a later time. On the other hand, active attackers are those who actively engage in manipulation or disrupting the drone's communication and operations. These attackers can employ a variety of techniques, such as injecting malicious code or signal interference to compromise the security and functionality of the drone. Unlike passive attackers, active attackers pose a more immediately and direct threat, and they have the capability to cause harm or direct interference with the drone's operation in real time. It's important to distinguish between these two types of attackers as the researcher implements vulnerabilities in cases where they had no physical access to the drone, and in other cases where they did. Let's start with the wireless phishing layer. The security analysis conducted without physical access to the drones focuses on revealing vulnerabilities present in the cyber-physical systems in this device. Researchers delve into the complex network of radio frequencies used by drones, aiming to intercept and decode the wireless signals transmitted between the drones and its remote control. As a passive attacker, a scenario was investigated in which an adversary lacked physical access to both the drone and the remote control. Instead, the attacker was limited to observing and analyzing the wireless signals transmitted during the drone's operations. This approach focusing on analyzing DG Oculus Sync protocol and its identification signal, known as DroneID. Let me briefly explain. DroneID is a unique identification signal emitted by DG drones during the operations. It functions as a kind of digital fingerprint that allows for the identification and tracking of a specific drone in airspace. This signal is used not only for drone identification but also for other purposes such as air traffic management and security. On the other hand, Ocus Sync is a communication protocol developed by DG using its drone in its drone for data transmission between the drone and the remote control, as well as for real-time video transmission. This protocol enables stable, high-quality connections even in environment with interference or high signal density. Additionally, this Ocus Sync can offer transmission range of several kilometers, making it like an invaluable tool for drone pilots needing to operate over long distances. Finally, the SDR, the software-defined radio, is a device that allows for the reception and transmission of radio signals using configurable software and hardware, rather than delicate traditional radio components. This means as SDR can adapt to receive and process a wide range of radio signals, from FM radio frequencies to frequencies used by Wi-Fi or Bluetooth devices, among others. By using SDR and a series of signal processing algorithms, we are able to implement a real-time DroneID receiver. This receiver allows of interception and decoding of DroneID signals, revealing not only the presence of these signals but also their unencrypted nature. The results of this analysis are both revealing and concerning. It was demonstrated that DroneID signals could be intercepted and decoded relatively easily, raising serious concerns about the privacy and the security of data transmitted by drones. Additionally, it was revealed that manipulating the transmitted locations information was possible, suggesting the potential and identity spoofing attacks or sabotage. This analysis not only provides a detailed insight into vulnerabilities present in drone systems, but also highlights the critical importance of addressing these vulnerabilities and implement effective measures to protect the integrity and privacy of transmission data. So this underscores the needs for greater awareness of drone security and a more proactive approach to addressing the risks associated with their use. But I'm going to explain section by sections. The first one, DroneID, the receiver. This section describes the implementation of a DroneID receiver, which is capable of capturing the signal transmitted by DG drones and processing it to extract information such as at the drone and pilot's locations. It utilizes a software-defined radio, the SDR, to capture the signal and a Python process to decode it. The implementation includes a step-by-step analysis to derive unknown parameters of a proprietary protocol from the radio signals. Additionally, it mentions that the receiver continuously scans two frequency bands, 2.4 GHz and 5.7 GHz, to find DroneID package and process them in real time. Now, imagine that the DroneID receiver is an antenna that captures signals sent by drones. This receiver is designed to listen to those signals and understand what information they contain, such as the drone and pilot locations. So it uses a special type of technology called the SDR to do this. So along with computer programs that helps process the captured information and turn into something that we can understand. The second, spectrum analysis. This part details the spectrum analysis of DroneID signals. It describes how the specifications of the Ocus Sync and DroneID protocols are not public, but through reverse engineering, it is determined that these protocols use modulation techniques and parameters similar to the LTE, the long-term evolution. The spectrum of a DroneID radio frame is shown and its components are explained, including synchronization symbols and OFDM, orthogonal frequency division multiplex data. So the spectrum analysis is like looking at a graph that shows what the signals sent by drones look like. It helps understand which parts of the signal are important and what information we can obtain from it. It is like examining a drawing to understand how it works. The demulation. Here it explains how radio signals are demulated to convert them into bits and bytes. The steps of time and frequency synchronizations, channel estimations, and FDM subcarrier demolition are described. So it's detailed how cyclic prefix is used for time synchronization and frequency offset correction using Sadov-2 sequences. It is also describing the demolition of the mean subcarriers which are modulated with quadratic. It's called Quadratic phase shift keying, QPS key. When we listen to a drone signal, in a special from that we can directly understand, the emulation is like translating that special format in something we can understand, like converting a foreign language into our language to understand what it says. Decoding. This section explains how the emulation data is decrypted to retrieve DroneID information. It describes how data is encrypted and encoded using gold sequences in a turbo encoder. The description and decoding process is applied to map the resulting data onto the DroneID structure. Once we have translated to signal or something we can understand, we need to decrypt what it says. This involves understanding data being transmitted and organizing in a way that makes sense to us. It's like reading a secret code to uncover the hidden message. The performance. Here the performance of the DroneID receiver is discussed. In details how different models of DJI drones were tested and how these receivers successfully decode DroneID transmission in real time. Flaky flat resolution and location information update frequency as mentioned. The limitations of receivers such as limited range and sensibility to interference are also discussed. And finally, the results. This section presents the results obtained from the analysis and is confirmed that the DroneID transmission are unencrypted and the drone and pilot location information can be encrypted and decoded. Experimental conducts to test the possibility of spoofing the pilot's location and disable DroneID transmission are discussed, confirming that these actions are feasible. So in this article, it's mentioned that researchers are able to perform spoofing, which is a technique using in cybersecurity to falsify or impersonate information to on-device system, person, or device. This technique is used for various purposes, such as identify the theft and undirected access to systems or data manipulations. So, manual static analysis is a process in which researchers examine the firmware of a device, in this case the drone firmware, statically, meaning without executing the code. The goal is to understand the structure, operation, and potential vulnerabilities on the firmware. Here, the researchers use standard firmware analysis tools such as Grida, Beamwalk, and Hexadecimal Editor and the DJI firmware tools. These tools allow them to examine the binary code on the firmware and extract relevant information. They focus on analyzing different parts of the firmware, such as the drone flight controller. This allows them to understand the features and functionalities of the drone, as well as identify potential vulnerabilities. An important part of this analysis was understanding the structure of DJI Unified Metadata Layer, that is the DUML protocol, which is used to communication between the drone and the remote control. This knowledge was crucial for the subsequent dynamic analysis. During the static analysis, the researchers discovered a vulnerability that allows them to bypass DJI firmware signature and gain privileged access to the device. This vulnerability was identified by examining the drone's bootloader and SDRIH configurations files. Based on these findings of the static analysis, the researchers developed custom firmware patches to exploit this discovered vulnerability. These patches allow them to make arbitrary changes to the firmware code during the drone's boot process, thus bypassing DJI firmware signature process. Now, all of this was done for the purpose of understanding in detail how the drone operates, what components are present in this firmware, and how they interact with each other. This provides them with an overview of the system architecture and potential areas of vulnerability. Subsequently, the discovery of a vulnerability in this drone firmware that allowed them to bypass DJI firmware signature and gain privileged access to the device. This finding was crucial because it revealed a weakness in the system security that could be exploited by an attacker to gain control over the drone. Based on the discovered vulnerability, the researchers developed custom firmware patches that allow them to exploit the vulnerability and gain privileged access to the drone. So, on the other hand, in dynamic analysis, specify the fusion process. It's an automated technique for discovering software flaws by providing the target under the test with potential invalid inputs. Here is a detailed breakdown of how its analysis was carried out. First, the DOM protocol was identified as a suitable target for fusing due to its central role into the configuration and internal communication of drones. The DOM protocol is used to configure the interior drones and is employed by an internal components of the drone for communication. A generation black box fuser was designed using a customer grammar to generate inputs for the DOM protocol. Subsequently, the fuser and the user interface Oracle were implemented in approximately 4,000 lines of Python code. The fuser can be configured to conduct test either through to the drone USB serial connections or wirelessing while connected from the radio control serial port. The UE Oracles uses internal Android tools such as ADB and UE Automator to interact with the DJ application on the smartphone automatically and determine in the application states and the data reported into the application's interface match expectations. For independent physical campaigns were tested using different drones and radio controls. The setup requires for testing teams to be on the same Wi-Fi networks as the Android phone, and the drone had to be connected of that team. The phone connected to the radio control, which is turn establishes the drone, which the drone. Tests were conducted using drones such as Mavic Air 2, DJI Mini 2, Mavic 2 Pro, such as well the RC231 radio control. To fit their results, approximately 7.8 million test commands were executed, generating by enumerating all DOM commands. 15 software flaws were identified that caused crashes or unexpected behaviors. Flaws included vulnerabilities such as arbitrary command execution, modification of the drone serial number, and intelligent and ADB search with rules privileges. So finally, the results. In the discussion section, the discussion revolves around upcoming standards for drone identification and localizations, emphasizing the importance of transparent communication regarding data transmission, especially the terms of privacy risk. The analyst revealed vulnerabilities in both the drones and the remote control, the RC, including critical security flaws that could lead to crashes during flying. Deficits in the implementation of secure firmware updates were also highlighted. Recommendations are made for manufacturers to conduct additional testing, such as fuzzing, to identify and mitigate errors. The potential of activity attackers to inject their own DroneID package to falsify drone location as acknowledged, along with the lower adoptions rate of security measures by other manufacturers and the lack of public documentations on their security measures. So in summary, the results demonstrate that DJI drones exhibited significant differences in terms of security and privacy, highlighting the need to address this vulnerability to protect both operator and the general public. It is emphasizing to avoid falsehoods and generalizations by believing in that just became its a large company. It encrypts and protects all the information we're involved in. There is a request from the company to correct these flaws, and users are also urged to be more critical about their security and protections.